Okay, let me thank the organizer for continuing this very nice meeting. So I'll be talking about entanglement entropy of some strange metal, model of strange metal. So this work has entirely done by Shantanu, who is a graduate student at IISc, and I acknowledge collaboration with Surojit, Genuine, and Shubhit. Okay, so let me get into the definition. So well-known definition of entanglement. So if you have a pure state, then essentially you have a system which you divide into, let's say, two subsystem A and B, with A having a length linear dimension LA. So you define the entanglement this way, that you define a reduced density matrix, and then you define the entropy of entanglement for that reduced density matrix. You can also define this Renyi entropies, which are easier to calculate, and I will be mostly talking about the second Renyi entropy. So one very famous example is if you just take this triplet state of two qubits, then if you look into one of the qubit as a subsystem, then you get from this the log 2 entanglement. But why do we care about entanglement in condensed matter physics? The reason is that there are some intrinsic quantum correlations that are very hard to obtain from other standard probes that you can directly obtain from entanglement. So you can, and this can work for even high energy states and ground states, and you can detect various kind of symmetry breaking critical phenomena and topological signature from this. So one example is that you can distinguish very highly entangled and low entangled states, so-called volume law and area law entangled states in D dimension. And the way to sort of understand a caricature way is that if you have many Bell pair between extensive number of Bell pair between the subsystem and the rest of the system, you get a volume law. Otherwise, if it's only near the boundary, then you get an area law. Now, this area law is not the only thing. So it turns out that this correction to the area law also can give you interesting informations like about symmetry breaking and topological order and other characterization. And beyond the area law, there is also some other universal aspect which appears for gapless systems. So for example, let's say gapless fermions or critical bosons in one-dimensional systems, so which is, let's say, defined by a 1 + 1 DCFT. So it turns out in this case there is a violation of this area law through a log term, which is log LA. However, what is most interesting is the thing that sits in front, which is the central charge, which is sort of the universal aspect of this theory. For example, a standard example of free fermions or even interacting fermions in 1D, Latinger liquid, this C is 1. Now it turns out that this argument you can take into higher dimension, and this logarithmic violation continues to hold for free fermions even in higher dimension, and this is expected to hold also for interacting Fermi liquids. So there is another interesting aspect of this, this logarithmic violation. It turns out that the same low energy degrees of freedom, that is these quasi-particles in this system, controls the low energy entropy and also the entanglement. So as a result, they are actually, this entanglement and entropy is connected through a very smooth crossover, which can be defined through a thermal length, which goes to infinity at 0 temperature. And it, when the length, the subsystem size is smaller than this thermal length, then you recover entanglement. Whereas if you go to the higher temperature limit, sort of where LA is larger than this thermal length, you recover thermal entropy. So this entropy and entanglement are smoothly connected. So the question that we are asking, that what happens to metals with, so now these are all for sort of metals with well-defined quasi-particles. The question is what happens to metals without quasi-particle, which are, let's say, not described by local CFTs. So one example could be, although we don't really know, is this kind of famous strange metal state in these cuprates, high TC cuprates, as a function of temperature and hole doping. One has this strange metal which is characterized by this non-Fermi liquid resistivity. So motivated by this, what we are going to do, we are going to look into a model which is this one-dimensional Yukawa-Sazdev-Kitaev model, and which has basically a one-dimensional model with two Fermi points. However, at this Fermi point, there are no quasi-particles. So it's a critical Fermi points without quasi-particles. So similar thing has been studied in 2 dimension, and it has been shown that this kind of non-Fermi liquid captures many of the properties of this strange metal non-Fermi liquid. So very quickly, the model essentially is this large N model, where you can think of the model as a collection of quantum dots. Each quantum dot has some N flavors of bosons and fermions, and this is on a lattice. Okay, and there are parts where fermions hop from one quantum dot to another, and the bosons also move from one quantum dot to the other. What is most important here is this Yukawa coupling between the bosons and fermions. So this Yukawa coupling is random, sort of a random Gaussian number, and also there is a spherical constant. So it turns out because of this random Gaussian coupling, and when you take n going to infinity limit, this model is exactly solvable. You can essentially calculate all possible properties, equilibrium and non-equilibrium of this model. So for example, you can obtain the exact electronic self-energy and Green's functions, bosonic self-energy and propagator, and also what is called the boson thermal mass. So this is the phase diagram of this model using this large N theory. So what we will find that there is a point which is a quantum critical point where this boson thermal mass basically goes to 0 as a function of this parameter gamma, which tunes this spherical constraint. And on the right side of it, you have a Fermi liquid where the mass, the boson thermal mass is non-zero at finite temperature, and you can show that they are basically, this critical point is a strange metal and the Fermi liquid is like a standard Fermi liquid. So the question is that what happens to this kind of entanglement and thermal crossover in this system. So what we are going to do, we are going to calculate in this model exactly in the large N limit the entanglement entropy of fermions in a subsystem. Now in this model, because there are both bosons and fermions, when you calculate the entanglement of entropy of fermions, so there is a non-local entanglement like this non-local Bell pairs between A and B subsystem. However, because there are bosons, so there is also entanglement that will be remaining between fermions and bosons in a subsystem itself. So this is the quantity we calculate, and what you expect that this non-local entanglement will have some, maybe some logarithmic violation, whereas the local entanglement will go like volume law. So we use some method that we have been developing over the years to calculate entanglement entropy of strongly interacting system using imaginary type path integral, and this is the result. So what is plotted here is this entanglement entropy as a function of subsystem size for a 1D system at different temperature. As you can see that as temperature increases, it sort of crosses over to a thermal entropy. So what is amazing is that this entire, all the curves at different temperature and the subsystem size, you can collapse into a single curve using a universal scaling ansatz, where again there is a length scale that appears. Okay, so you can collapse all the curves into this, and it turns out unlike the Fermi liquid, this length scale, when you collapse the curve, it actually doesn't diverge at 0 temperature. In fact, there is a residual length scale that remains even at 0 temperature. And more remarkably, this universal curve you can actually fit with a CFT-like form, although it's not a CFT, and with a coefficient which is like some effective central charge. And for this strange metal, this effective central charge turns out to be 1.6, okay, which is much larger than this value 1. So you can also understand various crossovers. So you can actually essentially recover what I said earlier, that recover the crossover between local entanglement between fermions and bosons, non-local entanglement between fermions and rest of the system, and also the thermal entropy from this entire formula. And you can do the same analysis for a Fermi liquid, and what you find is that this effective central charge, which becomes quite large, 60% higher than the non-interacting value at the critical point, is also substantially larger even in the Fermi liquid side. And with that, let me just conclude with this slide. Thanks.
Questions?
Yeah, it's because of this theory. I mean, in general, if you have an interacting 1D system, it's absent because this is Luttinger liquid. This is not a Luttinger liquid, but because of the non-Fermi liquid interaction, you can show that it is 0. So I showed the self energy, which is goes like square root of omega. So you can show that that implies that there is no quasi-particle at the Fermi point.